Hello, everyone, and welcome to the first lecture of the fourth week. This week we will be looking mostly at series, their properties, and common tasks involved with them. I'm very sorry for the delay of the lecture. Um, a few, well, um, personal but also technical things came up which caused the delay. We're very sorry, and we'll do our best to be in time for the next lectures. All right. So this is the first presentation on series, the first chapter, and we will be looking mostly at the basics and fundamentals in this particular lecture. So in the beginning, I will explain to you what a series actually is, how it's defined, what its relationship to a sequence is, and then the core aspect will be going over the basic mathematical properties and to get to know some very famous examples of series which are useful in mathematics all the time. Okay, so let's start with an example. Here I have a sequence for you. It's the sequence of odd numbers which can be expressed as 2n minus 1, with the first term being 1. Now the question is, what happens if you sum up the first, let's say, a odd numbers? So you, instead of looking at your series one term after another, you define each term to be the sum of all the previous terms of the sequence. So let's take a look at what happens. In our example, well, 1 is 1, like the sum of the first term is just the first term. 1 and 3 equals 4, 1 and 3 and 5 equals 9, 1 and 3 and 5 and 7 equals 16. This can easily be continued. And well, if you look at the results on the right hand side, a suspicion should find its way into your mind. So you see, when we sum up all the odd numbers, we get an ordered sequence of all the square numbers. This seems somehow odd, doesn't it? So, is this a true relationship or is it just pure chance? We can prove this. We will do this in a moment. But first of all, let's just summarize what we did here. So we took our sequence, the sequence of odd numbers, and then what we did is we summed up a variable number of terms. And if we now take this variable as the variable of our new sequence, the sequence of the partial sums of the initial sequence, well, we get a series. We get the series over the initial sequence. So we've established that the series is just a type of sequence which is defined as the increasing sum of all terms of an underlying sequence. Now, our initial sequence here was the odd numbers, and we had the hypothesis that the series over the odd numbers yields the square numbers. So what we currently have is a recursive definition of our series. We say, okay, we add up all the odd numbers that we have so far, and to get the next term, we add a new odd number, the next higher odd number. And what we now want to do is we want to find a closed form. So saying we just add the next odd number every time to get a new number would be a recursive definition. But if the series actually were to be the square numbers, so let's say capital A of n equals n squared, then this would be a closed form or an explicit form. And we can try to prove such a form if we already have a hypothesis how it looks like. So here the proof would use complete induction, and your hypothesis is that the kth term of your series is equal to the kth square number. So the sum of your sequence until the kth place is equal to k squared. And you, of course, need to induction start, so you need to prove that for a particular case it works. We can use 1 for that because 1 equals 1 squared. And now we have to do the induction step. So we have to show that for the case of k plus 1, it works given that it works for k. And if you look here at proof, you can see what I did. I plugged in the term k plus 1. So we, on the left-hand side, in the induction step, we sum all the odd numbers until k plus 1. And, well, this is nothing else than the sum of all odd numbers up until k plus the number k plus 1. And now, given our induction hypothesis, we can plug in k squared for the sum of all odd numbers until k, and we get the expression k squared plus k plus 1, which is just the first binomial. So we can express this as k plus 1 squared, and this is just what we're looking for. So given that the first k odd numbers sum to k squared, the first k plus 1 odd numbers sum to k plus 1 squared. Thus we have proven a closed form. Now, of course, a question which naturally comes up quite often when doing such things is, what is this good for? Why are we doing this? And initially, defining series can be kind of weird, like it falls out of nowhere. It's kind of important to keep in mind that a series is nothing else than a sequence. It's a special type of sequence, which is recursively defined over another sequence. So, for example, instead of saying, hey, we have a series over the odd numbers, you could define the square numbers just as the square numbers. However, sometimes there is no way to explicitly express a certain sequence. So sometimes there's sequences which can only be expressed as the series of another sequence. So if we have such a sequence at hand, well, the idea of a series makes much sense because it's the only way for us to express this kind of sequence, the series of simpler sequence. And when we work with series in mathematics, or especially in physics, but also some other related scientific fields, which can also come up in cognitive science, there's usually 3 problems about them which tends to come up. And those 3 are the convergence behavior, the limit, and the closed form. Although it should be noted that the first 2 are far more often important than the last one. So with convergence behavior, this means if you add the infinite number of terms all on top of each other, do you get a number or do you get definite or indefinite divergence? And then, of course, if it converges, the question is, what is the limit? Oftentimes, we want to know an exact number to which such a series converges. And sometimes it is useful to know a closed form. So sometimes we have a series which is, well, of course, the partial sums over the underlying sequence, but for pragmatical purposes, it is kind of difficult to work with this recursive definition. So we want a closed form in order to be able to explicitly calculate the term at any given n. Now, let's go over some very simple properties of series, which are the first things you have to take into account when you encounter a series and you have to discuss convergence behavior and limits. So, if a series diverges, usually, from my personal experience with working on series, proving divergence is usually easier than proving convergence. But nevertheless, a necessary condition for a converging series is that it is a zero sequence. This means that the underlying sequence has to converge, and it has to converge to zero. And the intuition behind this is quite simple, I guess, because let's say you have a sequence which converges to 5, the number 5. If you make a series out of it, in the limit, every single term gets arbitrarily close to 5. And if you sum up an arbitrary number of 5s, you will always diverge to positive infinity. And this is true for any positive or negative number. If you converge to a positive or negative number, and then you make a series out of it by adding an infinite amount of this number over and over again, you always will explode to one of the two infinities. So in order for the infinite number of terms in the end to yield a finite number, they kind of have to approach zero. Although this is a necessary condition, not a sufficient one. This means if a sequence does not have the property of being a zero sequence, it definitely diverges. It does not fulfill the necessary property to be a converging series. However, you don't know if it converges if it fulfills the property. There are zero sequences which still diverge. And the second property I wanted to go over is boundedness. We already talked about this in last week. Boundedness is a sufficient criterion for convergence. So if we have an entirely positive or negative underlying sequence, even a one-sided bound suffices. The idea of this is that, well, you are constantly adding new terms, and especially if you imagine an all positive underlying sequence, this means that a series will rise monotonously. So every new term will be larger than the previous one. And if you have the property that the series is always rising, but at the same time there's an absolute upper bound, this means that it has to converge, right? So if you can prove there's a bound and the series is monotonous, you will definitely converge, just by courtesy of logic. The reason now why convergence is more challenging to prove than divergence is that finding such an upper bound can be quite challenging. It can be difficult to prove that. I mean, assume you have a convergence series which is rising. Why on earth shouldn't all the infinite number of terms at some point exceed 10 or 50 or 5,000, right? So this can be a more difficult property to prove, but more on this in the second lecture. So if we've proven that a series is converging, sometimes the limit can be of interest. However, this problem can get like really difficult. Like just because we know a series converges, we don't know its limit. We can find bounds, like we can say, okay, if we sum up the first 50 numbers, we get this number, so our limit has to be above it. And we can also find upper bounds saying, okay, it can never exceed this number. But finding the exact number is usually a very difficult problem. And most of the time, when proving the exact limit of a series, it involves a lot of trickery. Just by taking a similar series where some super smart mathematician in the 19th century came up with some crazy ass proof. But more on this in chapter 2. Like this is a topic in itself. And now to the last problem, the closed forms. So closed forms are rarely of interest in our application, and usually when they are of interest, then convergence behavior is trivial. So usually closed forms are of interest, for example, when we were adding the odd numbers. The point is that, like, if we build the series over the odd numbers, then it's clearly diverges, right? The numbers get bigger and bigger. This is obviously trivially diverging. So usually we care about closed forms not really in order to model something or understand how behavior towards infinity works, but we care about it if we want to understand the, let's say, underlying mathematical properties at hand. So, for example, understanding that the difference between two square numbers is always an increasing odd number. I don't know, this helps find regularities in mathematics, but it doesn't really care about infinities or anything. It's just about um, finding patterns. So it's a quite a different problem to the problem of convergence, divergence, and limits. Okay, so let's get right into it. We will cover now two of the most important series in mathematics, which most of you probably will have at some point heard about, at least nominally. Um, but let's start by introducing it lightly. So, let's start with the sequence, the initial sequence. Here we have a of n is 1 over 2 to the power of n. This would be equivalent to 2 to the power of minus n. Now let's look at our sequence. We get a couple of terms here on the slide, and you can see it's just the reciprocal values of the powers of 2. So we get the next term by halving the previous one. And now naturally the question arises, okay, we have a sequence here. What is the corresponding series? And this one right here is a very special one because it has a, well, not unique, but characteristic property, which is that two consecutive terms always share the same ratio, right? So if you look at it, any two consecutive terms, the first one will be twice as big as the second one. So this property that the ratio between two consecutive terms is invariant is called a common ratio. And this property is quite important even for, or I mean, I guess this ratio in general is quite important even for sequences which don't have a common ratio. But looking at this ratio in general is a very important property with series. But here I have a little proof which shows you that in a general case, the common ratio of our sequence is always a half. So if you take a of n and a of n plus 1, just general terms which are consecutive, one is 2 to the power of minus n, the other is 2 to the power of minus n plus 1. And if you just cancel out the powers, you can just simplify to 2 to the power of 0 divided by 2 to the power of 1, and thus you get 1 over 2, which is now the common ratio of this geometric series. And if we, in general, have the property of our initial value, a0, and a common ratio r, which is fulfilled by every single term of the series, this is already defining a geometric series. And geometric series are very well studied in mathematics, and we know a lot about the convergence behavior, which I will go over in a second. However, we will not prove all of the foundations in mathematics that led to the knowledge which we're about to look at. Okay, so now let's look at the proper definition of a geometric series. You technically need three things. You need a common ratio r, and you need an initial value. And additionally, it has to be of the form which is denoted on the slide. So R has to continuously be raised to a higher power. Might surprise you, but there's actually other kinds of sequences which also have a common ratio and are not a geometric series. But a geometric series looks like this. And now the cool part is that we can read out its convergence behavior and its limit just out of a formula. We know that if the absolute value of R, so regardless of whether it's positive or negative, is greater or equal to 1, the series diverges. And this kind of makes sense, right? Imagine you plug in a number bigger than 1 into R, and then you can continuously raise it to a higher and higher power. Of course, the numbers go to infinity. The cool part is if it's smaller than 1, the absolute value, the series definitely converges, and we even have a formula for it. It's the formula 1 over 1 minus r. And regardless of what r is, as long as it's smaller than 1, this always gives you the limit of a geometric series. So now let's look back at our example. Our sequence was 1, a half, a fourth, and so on. And if we build the sequence of partial sums, so basically the series, you can notice one odd property, which is if you take the first term, 1, and you calculate the arithmetic mean between 1 and 2, you get the next term, which is 1.5. And if you, again, take the arithmetic mean between 1.5 and 2, you get 1.75, and so on. So this property continues. So the distance to number 2 is halved by every turn. And incidentally, 2 happens to be the limit of the series, since 1 over 1 minus a half is 1 over a half, so 2. So this means that the distance to the limit of the series is, well, halved in every term. And, well, this is a common property of the geometric series. Of course, if your r is not a half, but a third, then the distance will always be reduced by a third. But this general property always remains that you always reduce by a certain percentage of the remaining distance to your limit, and by continuously doing this, the distance to the limit shrinks to 0 when you converge. Now, I'm proud of you for sticking around for so long. You probably deserve a little break now. And if you're done with the break or you're feeling super motivated, just grab a pen, a piece of paper, and solve me the following sample exercise. Assume you have a geometric series with a common ratio with an absolute value above 1. Tell me the type of divergence this series has. And also tell me what special case comes into play when r equals 1. Pause the video, take a little break, think about it, and if you work on this, I will share a possible solution after the summary. Okay, now let's get to our second exciting, famous series. It's called the harmonic series, and its definition is quite simple. So the sequence which is underlying is just a sequence of 1 over n. So get 1, a half, a third, a fourth, and so on. And the series is just, again, the partial sums. Harmonic series is also commonly called capital H. And compared to the geometric series, there's not like a million variants depending on what r is, but like this particular sequence is called the harmonic series. And here in the figure, you can see a plot of the harmonic series. The partial sums of 1 over n. And interestingly, you can see a upper and lower bound of logarithms. So the small little black lines are just logarithmic functions with different bases. So this kind of already gives a little hint on where we're going with this. If you didn't already know, I'm gonna assume your initial feeling about the harmonic series, so one and a half and a third and a fourth and so on, is that it converges. I mean, this is a very reasonable, I would say, gut feeling about the harmonic series. I mean, I guess similar to the geometric series, every term gets smaller and smaller. We have a zero sequence in hand. Why shouldn't it converge? But like, try to prove it converges. I dare you. Um, the weird part is, even though it's rising slowly and slowly and continues to become slower and slower, it actually never converges. Impossible to find a boundary. And there is actually arithmetic reason for this. You can prove that it diverges. And if you don't believe me, I'll go over the proof now. So, um, in order to prove this, I will need a little helper series, which I'm defining right here. So assume the series looks, our helper series looks like this. It's 1.5, and then 1 over 4 plus 1 over 4, and then 1 over 8 plus 1 over 8 plus 1 over 8 plus 1 over 8, and then 8 times 1 over 16, and this would continue with 16 times 1 over 32, and so on and so on. So what basically happens is you look at the denominator of your term. You look at the harmonic series. You look at the denominator of the term, and if the denominator is not a power of 2, you just round it up to the next power of 2, right? So technically here you would have a harmonic series which goes like 1, 1 over 2, 1 over 3, but 1 over 3 is rounded up to 1 over 4. I mean, 1 over 3 is rounded down to 1 over 4, but 3 is rounded up to 4. And then 1 over 5, 6, and 7 are all rounded to 1 over 8. And by doing this, obviously, we reduce the size of the numbers, right? Some terms of the series stay the same, and some get smaller, right? 1 over 5 is obviously bigger than 1 over 8, the term which is replaced with. So here we have a series which definitely is smaller than the harmonic series. And now, if we take the second term, and then the third and the fourth term, and then the fifth to eighth term, and so on, we always take terms with the same denominator. We can just add them together, right? So 1 over 4 plus 1 over 4 is a half, and then 4 times 1 over 8 is a half, and then 8 times 1 over 16 is a half, and then 16 times 1 over 32 is a half. So we can reduce this series to the series 1 plus a half and a half and a half and a half. And this is a trivially diverging series. Now, this looks more diverging than it actually is. The reason that it looks so quickly diverging, but actually isn't, is that at some point, in order to sum up to 1/2, you get a lot of terms, right? So the number of terms you need to get to a half is rising exponentially. But you always get them, right? There's an infinite number of terms, so you can also generate an infinite number of terms 1/2. And since this series is diverging, and the harmonic series is clearly larger than this series, the harmonic series must obviously also diverge. So as shocked as you might be that the harmonic series diverges, it actually definitely does. And if you think back to the initial figure, the harmonic series was bounded by logarithms. And as you know, logarithms all diverge to infinity as functions, but they do so incredibly slowly. And I guess the same thing is true about the harmonic series. In a sense, you can look at the harmonic series as the discrete sequence counterpart to the function of a logarithm. The two are very closely related to one another. Um, okay, so to explain the intuition behind this barely diverging series, it means that if you strip away a part of the series, 1 over n, if you take away just a little bit, it will quite quickly start to converge. Take the example 1 over n squared, the series over 1 over n squared. This converges super quickly. Like, the limit of this series is smaller than 2. And I mean, I guess this is pretty interesting or unexpected, given that 1 over n just completely diverges. It goes off to infinity. And if you just square the denominator, it suddenly has a super small limit. I mean, consider that the first term is 1, and then the sum of all the remaining terms is smaller than 1. Pretty interesting in my opinion. Proving that is pretty difficult, but if you're interested in this, is another thing I would recommend you looking up. It's also known as the Basler problem. I guess the actual value of this sequence was proven by Euler the first time. Uh, the arithmetic value is pretty amazing. There's um, random pi's and e's coming up all over the place. There's even more to it. If you look at the series 1 over n to the power of s, so let's say you just raise n to a certain power. If the power is 1, right, you get the harmonic series. So 1 and 1/2 and a third and so on. And if the power is 2, you get the series I just talked about. 1 over 1 and 1 over 4 and 1 over 9 and 1 over 16 and so on. So the additionally remarkable thing about the harmonic series is that if this exponent is any number larger than 1, the series instantly converges, right? So if you, instead of 1 over n, you take 1 over n, the power of 1.0001, it immediately converges. And this idea of the harmonic series just barely diverging makes it a great lower bound to prove divergence. Because if your series diverges, chances are it does so faster than the harmonic series, which would make the harmonic series a great lower bound to say, okay, look, my series is larger than the harmonic series in all terms. Obviously, then my series must diverge. All right, thanks for sticking around so long. I now have a second sample exercise for you, which is tailored to the harmonic series. It looks like the following. Now, consider a series G, which is technically just the harmonic series, but we omit every even value. So instead of 1.5 and a third, we just get a third, a fifth, a seventh, and so on. I want you to figure out the convergence behavior of this series. Again, take a small break, take a pen, a sheet of paper, think about it for a bit, and afterwards we will go over the solution. The final subject I want to touch upon in this lecture is the idea of alternating sequences. I'm not gonna go into much depth about it, but it's an important distinction which is made, which is important to know. So all the series we considered so far were over sequences which were either all positive or all negative. However, there's also sequences which are alternating. For example, if you take the harmonic series and instead of adding everything, you just create the alternating harmonic series. So you subtract every second term instead of adding everything, then it immediately converges. And I guess this makes a lot of sense because you get your first term, which is 1, and then your second term, which is a half. And then you continue adding and subtracting terms which get smaller and smaller. So obviously 1.5 give you absolute upper and lower bounds for the convergence of your series. I guess, of course, having upper and lower bound is not a sufficient criterion for convergence, but believe me, this converges. Yeah, and it only converges because it's alternating, right? And in those cases, you oftentimes the convergence of the alternating series doesn't really interest us because um, an alternating series very easily converges, right? This is really difficult if things get added and subtracted continuously. Oftentimes, when having alternating sequences, we are interested in absolute convergence. So oftentimes the problems which arise with alternating sequences also include taking the absolute value of every term and basically treating it as a all positive sequence. So there the distinction would be made that a series might converge, but does not absolutely converge. For example, the harmonic series. The alternating harmonic series, it converges, but it doesn't converge absolutely, because if you take the absolute values, you just get the harmonic series and it diverges. Um, However, in all positive sequences or all negative sequences, this doesn't really matter, and convergence and absolute convergence are synonymous. And we are not going to go much deeper into alternating sequences, but knowing this distinction is kind of good in order to not be shocked when encountering a not all positive sequence which gets a series at some point. All right, people. Now, this was all of the content. I'm gonna go now to summarize what we talked about. In the beginning, we defined what a series is. We found out that a series is just a sequence, nothing else, but it is defined recursively by the partial sums of another sequence. And now, um, what very, very often comes up in mathematics as a problem which needs to be solved, either for practical applications or theoretical ones, is the convergence behavior and if it actually converges the limits of these partial sums. If you take a bad example, so if you take a very ill-suited, bad-behaved sequence, um, these tasks of determining convergence and limit can be arbitrarily difficult. So it can range from um, absolutely trivial to unsolved problem of modern mathematics easily. And putting all of that aside, the two most important series which we know and which you are going to use all the time are the geometric and the harmonic series. Geometric series is a series which I guess it doesn't always converge, but it always converges for a common ratio below 1, which is the usual case which we investigate. Um, and the harmonic series is a great divergence series where the divergence is not obvious, but it's so barely diverging that it is a great tool for proving divergences of other series. And we have to bear in mind that there's alternating series, so series where not all terms are positive or negative. And with those series, we have to bear in mind that there's a distinction between convergence, so summing all the positive and negative terms together, and absolute convergence, which just means taking the absolute value of every term and then summing together. Okay, thank you for listening. I hope you, well, came through the lecture fine. Now, if you solved the sample exercises, I will quickly go over them. If you haven't yet, you now have the opportunity to post a video and come back and solve them if you like. I'm going to discuss the solution of the first exercise now. So in the first exercise, you were supposed to determine the type of divergence in a geometric series with common ratio greater or equal to 1. And this is, well, basically a task you can simply solve by thinking about it for a bit or just sketching yourself a small example. So I will quickly go over to what happens. Let's assume we have a positive r, so positive common ratio bigger than 1. Um, this means that, for example, if it is 2, in every new term, our previous term is doubled. So if we get an initial value of 1, we get 1 and 2 and 4 and 8 and so on. This clearly diverges. And if our initial value is negative, then of course we diverge again, definitely, but to negative infinity. So we either converge to positive or to negative infinity, depending on the initial value. On the other hand, if r is negative, it means like the ratio between two consecutive terms is negative and the absolute value is larger than 1. A ratio being negative, like the ratio between two numbers being negative, can only ever happen if exactly one of the two numbers is negative, right? So if you divide two negative numbers, you get a positive number, and if you divide two positive numbers, you get a positive number. But in order to get a negative number, and here we have a negative ratio, exactly one of the numbers has to be negative. This means that the series with a negative common ratio has alternating values. Like one has to be positive and one has to be negative. The consecutive terms must be alternating. And if we have a sequence which is alternating between negative and positive on every term and is clearly not converging to 0 since the absolute value of our terms are rising, then we have indefinite divergence. And if we look at the special case for r equals 1, well, we just get the constant sequence of our initial value. So let's say our initial value is 5, and the common ratio between two consecutive terms is always 1. Then, well, only 5 over 5 is 1. So we get a constant sequence of 5, which is obviously diverging. If you're actually of the opinion that the series over a constant number, so let's say the series over 1, which just yields the sequence of the natural numbers, 1, 2, 3, 4, 5, and so on, does not diverge, then you should probably take a look at the video I linked right here. But be aware, if you share this opinion, probably mathematicians are not going to take you too seriously. Okay, now to the second exercise. In the second exercise, you were supposed to show the convergence behavior of the series, which I showed you. So it was the harmonic series where you omit every second term. I've here written on a slide the two series. The first one is 1 plus a third and a fifth and a seventh, and the other one is the harmonic series. So what we want to do is we want to find an estimate for the harmonic series in order to make a comparison. So what we're going to do is we're going to take every second term of the harmonic series and increase the denominator by 1. So this makes a half into 1 and 1 over 4 into 1 over 5, 1 over 4 into 1 over 3, and so on. So we decrease the denominator of every second term. We don't increase it, we decrease it. And if we decrease the denominator, the terms rise. So this alternated way of the harmonic series, 1 plus 1 plus 1 over 3 plus 1 over 3, and so on, is clearly bigger than the harmonic series. And since the harmonic series is diverging, the series I'm here presenting to you is obviously also diverging. So The question is, how does this help us to determine the convergence behavior of G? Well, if we just multiply out a factor of 2 out of our new series, we exactly get 2 times G of n. So this means that taking our series G twice yields a definitely diverging series. And since a definitely diverging series has the limit value of positive infinity, this means that if it is equal to another series, just being off by a scalar of 2, well, it still has to be infinity. Because infinity divided by 2, you can't divide infinity by 2, but infinity divided by 2 is still infinite. This is not an arithmetic operation. If you didn't know that, this is one thing you can memorize. If something is diverging and then something else is equal to this times a finite scalar, it's also infinite. So if you get infinity equals 17 times x, x is also infinite. All right. I hope you understood the solutions of the exercises and they helped you in the understanding. And I wish you good luck in working through the other lectures. Hear you soon.